Thank you very much for your kind introduction. Ladies and gentlemen, you see the title of my speech here. Honestly speaking, I do not know why I'm in the fuels effect session, because I will talk about combustion, injection, and maybe a little bit of controls. So everybody who is looking for chemistry, I have to apologize. I can't serve that. So first of all, I have to thank my colleagues and co-authors who have participated by presenting this paper and the manuscript accordingly. I have structurized my paper according to start with some kind of introduction and motivation, why we think that investigating and improving in terms of fuel injection is still worth in view of the upcoming challenges which we are facing. We do so also at AVV, and therefore I'd like to introduce to you and describe to you the hardware which we developed internally. Then I will come to some experimental results, first from the scientific lab and then from the engine test bench. And finally, I will end up with some summary and conclusions of what we observed within these studies. As we have heard before, yesterday and also today, we are facing new emission norms and boundary conditions. So therefore, I have here an example of a vehicle in the C-class segment equipped with a 1.6 liter DI diesel engine, operating under an REDE-conform cycle around Aachen, which we have standardized there. So we see here, according to the vehicle speed, starting with some city driving, going to rural conditions, and then ending up on motorway operation and reaching for a certain period 150, 160 kilometers per hour, which is part of the current discussion of the upcoming RDE requirements. You see in the upper chart, you see the evolution of the Nox emissions as function of time, subdivided between engine out and then several states along the exhaust system. As you see here, and this is the representative example for a, let's say, compact or mid-sized car, which we currently consider as a very challenging situation, because under current conditions these vehicles are mostly equipped with LNT technology. And as you can see here in the upper part of the chart on top, you see here the ridge spikes events when the LNT is regenerated, and you see how this is intensified once we reach the high-speed conditions on the motorway. So it is clear that this situation where we have to achieve this is not very helpful in terms of fuel economy, and you know that we have quite stringent CO2 standards to fulfill in the near future. So this is something which is not supporting such kind of strategies with regard to low CO2. So therefore this vehicle, as you know, due to the size, it is quite difficult due to cost and packaging reasons to equip a full-size SCR system on this kind of vehicle. So we have added here an SCR and DPF solution, close coupled, but as a passive system, so there's no active AdBlue dosing, so there's only a passive contribution of the SDPF towards the NOx reduction. And this is exactly what you see here stepwise. So we have in black the engine out NOx emissions. We have in gray then the first step downstream of the LNT. Then we come to the effect of the SDPF, and finally the red one is the tailpipe emissions, which is coming a little bit lower because we have the low pressure EGR downstream of the SDPF, so we have to further effect on the tailpipe NOx emissions. As I said, this vehicle is starting with engine out NOx emissions by around about 510 milligrams per kilometer, and if we would follow this trend in the RDE, it would most likely miss the upcoming RDE requirements with a certain significant gap. So in summary, this means we cannot fully rely on the exhaust after treatment, and especially for these kind of vehicles, it is necessary to improve the engine out situation, and therefore we talk about improved, enhanced FRE system capabilities, which is then the major part of my situation. Even if we consider a slightly larger engine, this type of engines, we see that with increasing weight, here reflected by the emitted CO2 emissions of a certain application, the distance between the target which we have to reach for such a kind of configuration with a passive SCR system, so a very cost-effective solution, will most likely not be able to meet the requirements which are currently under the latest status of discussion. So also here we have to work in order to improve a better EGR tolerance at higher engine loads, just referring to the motorway operational conditions which I showed before, and in order to have a good improved NOx soot trade-off, we have to work on the fuel injection equipment as well. And this is what we do, of course, for our customers, but also within our internal research. And this leads me now to the next step of my presentation, which is a kind of hardware description and the corresponding features. So what you see here is, meanwhile, our fourth generation of our in-house developed prototype experimental common rail injector. It's named High Force, which summarizes the three main features of this injector, meaning high injection pressure, going up to 2,500 bar injection pressure. The FO stands for fast opening, so we are relying on the benefits of a very fast needle opening and closing behavior. And the final RS of the name is relevant for the rate shaping capability of this type of injector. We have built so far up to 3 of these injector types. So following the current downsizing tendency, we are able to equip a 3-cylinder diesel engine, small diesel engine with that. But up to now, FEV board has not decided to go into mass production with that system, so no danger for the FAE system suppliers. As you can see here, this injector consists more or less of 3 major parts. So we have an actuation assembly on the top end, we have in the middle part the servo hydraulic assembly, and we have the nozzle assembly at the lower part. This is a somewhat more detailed view inside of the injector. So here we have the piezo module, which is an in production takeover of a system which is in the market. Then we have also the nozzle module, which is also only slightly modified in order to fit into our design. And then we have the central unit here, which I will explain in the next slide a little bit more in detail. So here's the functional principle of this type of injector. So we have here, at the beginning, we have the rail pressure which is available. This rail pressure supply is subdivided into 2 routes. On one hand, we have here the combination towards the pilot valve, which creates then a kind of control pressure. On the other hand, we have the rail pressure then here on the bottom in order to be utilized and converted into an active injection pressure. As I already said, we are aiming towards a very fast needle opening and closing behavior, and therefore the needle is spring-loaded, and as soon as the injection pressure, which is released from this control assembly here, exceeds the spring force, directly the needle opens with very fast velocity, and also in the same way it closes. And then we have the possibility with the piezo actuation to define the injection pressure, which is forwarded from the original source, from the rail. As I said, up to 2,500 bar, we can forward this directly, and it's used fully with the full momentum here at the nozzle tip in order to do the real fuel injection into the combustion chamber. So after the layout of this injector, after the design of this injector and the fabrication, we did, of course, first some investigations in the scientific lab. First of all, we started in a high pressure chamber. So this was installed, the injector was installed here in this high pressure chamber, and then it was investigated with a different kind of measurement equipment, including numbers of different types of optical investigations, which we figured out in order to evaluate and analyze and do the interpretation of the behavior of the spray as it enters the chamber. Here you see some pictures of that. So we have a water-cooled injector support at the assembly, and we have initiated the first investigations by only using a 3-hole injector, but which features the same hole characteristics and specification as later on the injector which is used on the experimental engine for combustion development. We were capable to simulate in this assembly engine conditions between 50, 80 and 100 bar pressure and chamber temperatures between 800 and 900 Kelvin. We did different kinds of variations regarding injection pressures and different kinds of actuations, so starting with normal square type, ramp type, but also boot profiles in order to see how the injection pressure and the injection of the fuel is taking place inside of this combustion chamber. Then of course we got a lot of pictures like this, movies with different kinds of optical measurements, and then we start to do the automatic post-processing to analyze the outcome of these investigations. And this is summarized in the first chart here on this page here. So we have here different cases. We have always investigated against in production series piezo injector. And what you can take out here, all of the important parameters which are classically used in order to characterize and interpret behavior of an injector, like liquid penetration length, lift-off length, and all spray angle. We see that especially if we move into the region where we have quite severe boundary conditions, meaning high temperatures and high pressures, the benefits of the fast needle opening get more pronounced, and we get significant benefits versus in production piezo injector. So this of course means that by these conditions inside of the combustion chambers, the boundary conditions for a proper combustion are improved, and we can hopefully utilize this in better efficiency or better emission performance as well. Only for completion, as I said, a wide matrix investigations of different configurations, either from the injection profile, as I said, different injection pressures, different injection profiles, but also different boundary conditions in the high pressure chamber were investigated. You can read more about the details regarding these typical parameters which we summarized here, like the lift-off length and the liquid penetration length. You can read this in the manuscript, which is in your hands, so I don't have to go into more details about this. Then, of course, with that very positive and very promising results coming from this high pressure chamber, we moved to our engine, single cylinder engine, in order to do investigations on the thermodynamic way. I have here the summary about the investigated load points. So in total we concentrated on 4 major load points in the part load area, which are representative for NEDC. But if you look at the data in more detail, you see that even for these points here in the lower 2 lines, that these are maybe even considering downsizing aspects as well as upcoming emission norms like RDE cycle, WLTP cycle, which are just in front of us. For today's speech, I only want to concentrate on these 2 load points in order to show you some of the results which we observed. The first example, we have here an EGR sweep performed at the mentioned load point, 2280 RPM and approximately 8 bar IMEP. We have selected certain settings, and you see that in this variation, the high force injector is compared versus the standard piezo injector, once operated without and once operated with a pilot injection. And you see here, if you look and go through the results, starting by the emissions on the left side, we can here more or less duplicate the emission performance of the piezo injector without pilot injection, so very good in terms of NOx smoke trade-off. On the other hand, if we look to the gases emissions, we have in terms of CO and hydrocarbons emissions, due to the quite rapid opening and closing behavior, benefits versus both counterparts. If we then go in the other parameters which are of high importance, like combustion noise, here indicated by the combustion sound level, we see that we are much better than the series piezo injector operated without pilot injection, and especially under high EGR rates, so meaning low NOx emissions, we are more or less comparable to the situation of a piezo injector with activated pilot injection. Also, the same is true more or less in terms of indicated engine efficiency. Also here, the fast and rapid fuel introduction also here results in a quite good combustion efficiency, which is more or less comparable with the situation of the pilot injection-assisted piezo injector. Combustion duration is, of course, then in between the 2 other counterparts. Going further, next load point is the higher load point. You see here, once again, more or less a similar behavior, so more or less quite similar emission performance with a a slightly better acoustic behavior of the injector, and also we identify roughly 1% better combustion efficiency of the high force injector versus the classical or the production counterpart. And if we go into some thermodynamic analysis and post-processing, we see that this is mainly coming from the second phase of the combustion, where we have somewhat faster fuel conversion in the second phase of the combustion as we have it with a classical counterpart. You also see here some results in regarding the burning rate and the cylinder pressure, which is related towards the comparison between both types of injectors. Summarizing this first sequence of testing investigations here in one slide. So we have here, as function of the different operating points, starting by the light load operation, going to the medium speed, high part load operation. We have here plotted and summarized the results, always adjusted to the same NOx output of the engine, so the specific NOx emissions are always adjusted to be comparable. And then we see different results out of the different strategies which have been investigated. So once again, we have the production injector without and with pilot, and the high force injector without pilot in contrast towards these. And you see that depending on the load point, there are slight differences. In the light load operational points, we often have significant smoke benefits. The calibration was intended to be at least similar or better in terms of NVH, so this was one dominating parameter. And then we have the results later on. See here, for example, at the highest load point, there's a slightly increased smoke emission, but significantly lower noise behavior. And in terms of the gases emissions, we always see that here the single injection event is favorable in terms of the fuel introduction, as we avoid the needle seat throttling during the pilot injection events, which is of course mostly a source for high hydrocarbon and CO emissions. Now, of course, as I said, these are investigations on a single cylinder engine with an experimental common rail injector, which most likely will not go into serious production. So the next important question is how to transfer this experience and this knowledge into the usage, which can be then used with available or upcoming common rail injectors which are on the market. And here, of course, the need is how to transfer this into software functionalities that make similar strategies like we have seen before, which were observed with the high force injector, which makes this possible with the help of software algorithms, which are then organizing and managing the fuel introduction. What we know, starting by the situation that we have to compensate for a somewhat lower cetane number, we know that we have, for example, we are starting without any effect, we are starting with identical injection timing. If we have no sensor which is able to compensate for that lower cetane number, then the first step is normally that somebody adjusts the beginning of injection control in order to achieve more or less a constant 50% point of fuel conversion. The next step is then, if you are able, with a model-based approach, also to control and to govern the maximum burning rate. So then you have a need to have a kind of active rail pressure control in order to adjust this as well. And then finally, what is more or less at the end of the road, which is the vision for the upcoming future, not talking about the next 5 or maybe 10 years, but maybe a little bit later, is that we want to be able to have a more or less complete combustion rate shaping by organizing the introduction of the fuel into the combustion chamber within one working cycle. And on our way towards this vision at the end, we investigated with different types of available series injectors. We evaluated the transfer of this behavior and this performance by the use of the software algorithms. You see here an example of that shown here. So now, what you normally typically know is, for example, starting by first point here with 900 bar injection pressure, either with one calibration you can be good in terms of combustion sound. So here the black bar shows that you are quite silent with the engine, but you pay this in terms of of high soot numbers, which is plotted here on the right chart for the same injection pressure. And on the other end, if you utilize the parameters and the capabilities of the FIE system towards a lower soot number, so optimizing in terms of soot, then you have the corresponding drawbacks in terms of the engine noise. And you see this here by this different curves plotted in gray or in black, how the combustion trace and the burning function looks like. And then the big thing is then how to manage then a kind of digital rate shaping here by actuation of the injectors, depending on the capabilities of the hardware in terms of hydraulic, but also electrical capabilities, but also the corresponding software algorithms which are available to control these functions. And here you see then the investigations according to different types of settings. And you see finally at the end of the day, there is a potential to use the higher rail pressure which is available with an acceptable level of noise by a modulation of the fuel injection as function of this digital rate shaping. And in the following EGR sweep, you see that here you can gain more or less the same functional performance as you would have with a single block injection. Summarizing this with in one chart is with software algorithms which are able to, on the base of a combustion pressure sensor which is monitoring the combustion chamber, and you have algorithms which allow to ensure that you have a constant degree of pressure rise. You see that it is possible to optimize to a certain extent under constant Nox emissions, like shown here, 0.4 gram per kilowatt hour at this 1500 RPM light load point. You can optimize the particulate emissions to a certain level by optimizing the combustion efficiency, getting a quite smooth, silent, quiet engine by controlling here this burning rate while utilizing high injection pressures with a given constraint on the maximum degree of pressure rise, here set to 3 bar per degree crank angle as the limit for the optimization. So this finally leads then to the summary here. So we are currently in the field operating the engines with more or less improved, more sophisticated conventional injection strategies, shutting off pilots more or less. Nevertheless, we are, let's say, linked to certain limitations. Our vision, our future is to have this in a more flexible injection characteristic to be able to design exactly the combustion pressure trace according to what is wanted. It can be separated. You can have the same operating point in a heavy acceleration with the second or third gear, but you can even have it under high-speed operation in the fifth or sixth gear. The boundaries are totally different. For one case, you might need a somewhat more stringent acoustic limitation. If the vehicle is already driving very fast, you have high wind noise, then of course you may accept somewhat higher DPD alphas in order to have maybe a more efficient or more emission optimized combustion process, and with the corresponding algorithms in the ECU, then you can design this towards a dedicated combustion trace. So, coming to the end of my presentation, to the summary. So, the upcoming legislative as well as market demands, they formulate the need for enhanced combustion behavior in terms of efficiency, emission behavior, as well as noise. We are quite sure that more or less all automakers will achieve the compliance with the upcoming emission norms, but the final customer will more or less select later on, not according to the emission norms, will select according to performance, fuel consumption, and maybe acoustic behavior. So therefore we would like to point out that comfort is a very important aspect for the upcoming time. The compliance with approaching emission standards cause multi-mode operation as well. So we have, of course, conventional adsorption modes, we have heating and regeneration modes, including rich engine operation, and in the future we also see additional functionalities like VVT or VCR on diesel engines, which impact the in-cylinder conditions very fast and very substantially, and where we have to react with the FIE system, as it is the most fast, most dynamic system in the engine, which can react very fast to change boundary conditions. The fuel introduction into the combustion chamber identifies the key parameter in designing the combustion process. And modern FAE systems, in conjunction with the corresponding developed enhanced control algorithms, they offer a significant potential, according to our point of view, in further optimization steps for combustion optimization, to meet upcoming requirements without stressing the exhaust after treatment too much. And with this, once again, I'd like to thank you for your audience, and I think we come to the Q&A afterwards.